I hope you're having a good day. Today we're going to talk about entity relationship modeling. I think it's probably the most important thing you should learn in our class today, or this semester, because if you learn to do this well, you'll be able to solve any problem. And once you produce a model, the conversion of that model into the correct set of database tables is very straightforward. So this is the part to concentrate on. This is the part that you should really try to learn well, so that you feel as though you can go into any problem domain, any problem situation, learn enough about it, understand it, know what's important to the users in that situation, and then design a solution for that problem. This is the way you'll do it. And I really have a maybe graphical orientation, so I really like this approach. And with that, I think we'll get started. Well, the ER model is our mission. You'll learn that entities are the same things as relations that you learned about in the relational model, and they match into tables, and they represent something in the world in the same way that a relation does. And so some of the same ideas of the importance of keys and foreign keys in relationships. And then we'll see some designs. Well, the diagram is, to me, the most important part of ER modeling. But the point of the model is to make a representation that we can use to talk about as designers and communicate with each other about all the data that we need in our system. And that's the purpose of the model. And in modeling, the power of modeling is in the ability to focus on individual pieces of the problem and solve those pieces, and then be able to aggregate all of those pieces into a complete model. And ER modeling really fits that concept very well. Well, so our main ideas or components of an ER model are entities, which are the same as relation, and attributes, which is same as columns in relations from the relational model, and then relationships, which is the same idea of keys and foreign keys implemented in the relational model. Well, an entity is data about something in the world. There are orders, customers, invoices, students, and so that is what an entity represents. And so an entity consists of instances of that entity, and it matches up exactly to the idea of a table. The instance of an entity is the row of a table. Often we or almost always we represent our entity as a noun. And there's all kinds of notations. I don't really want to get hung up on notation. Right? What I want you to know is an entity is a representation of the data from some object in the world. The rows of the entity represent actual data values in instances, or the instances of the entity represent actual data values from actual objects of that entity type in the world. So, for example, if we have an instance of student, it has values for the attributes of student, like student name, date of birth, address, phone number. So, entities, we make our models between entities. So we say a student is related to a course. And so there's lots of notations, and I'm going to be mostly using the crow's foot notation because that's what our book is using. Well, attributes are things that describe entities. And so in the relational model, attributes are columns. And so it's the exact same idea. And of course, one of the most important attributes we have is the key, the primary key. And so what that means, of course, is the idea that the values of an attribute or some collection of attributes uniquely identify every instance of the entity, every row in the table, every tuple in the relation. And so that is the basic idea of identifiers. We need to be able to know that we can identify every attribute in our system, or we can find all the data values in our system. We can find the data associated with every instance of every entity, and we do that through keys. And then we have other attributes that are required, and then that means they have to have a value. We have occasionally have attributes that are optional, but it's not that common. I guess it's optional to have a phone number, but it wouldn't be optional to have a date of birth, because everyone has a date of birth. It's just, would it be optional to report date of birth? I don't know. Anyhow, you can see where the true requirements of the problem really get involved. And the domain is an important concept. It tells us what are the possible values an attribute can take on, right? So date of birth can take on values in a reasonable range, probably something like 2014 or 1914 and above. But who's to say? Right, there's some domain that a value can take. Now, a good example of this would be state code. We know that there's two character state codes for all states. VA is the one for Virginia. PA is the one for Pennsylvania. I don't know what your favorite state is, but you probably know the 2-digit code for that state. And so if we have an attribute state code in an address in one of our tables, the possible domain of values for that state code are those 52-character abbreviations of state. And that is the possible domain for that attribute. And so it's good, we keep this information usually in a data dictionary. All this information is captured for every attribute. When we draw in our ER models, the things we focus most on are the relationships, which of course are the key and foreign keys in our entities. I will say that usually ERD is too complex to include attributes. And in real life, I have never really seen attributes on any of my ERDs, so don't need to include them for our class. But here's an example of an ERD with attributes. And either one of these is bad for me because all I really want to see on my model are my entities and the relationships among them. So I just want to see student. And then on the crow's foot model, I really don't need to see all those attributes. I know those attributes are there. If I want to know the attributes, I'll look at them explicitly. But that's not important to me. What's important to me is the structure of the relationships among the entities. And that's what I want to use the model for. But here is a way to represent attributes on models. Don't do it in this class. So what types of attributes are there? Composite identifiers, where a multiple key is composed of more than one attribute. If you think of the invoice line entity, where each invoice has many lines, and each line is associated with one and only one product. That composite identifier of line as invoice number and product number makes a lot of sense. Of course, you can never have a composite attribute, an attribute that couldn't be subdivided. I hate that, right? Although I have had to compromise over time for things like phone number. Nobody wants to really break out the area code, they say. So, okay, but to me, there's 3 attributes there, not 1, but I can be flexible. The attributes can't be subdivided. That's a must. A single valued attribute. That is an attribute value must be atomic. That means each variable can only contain 1 value. And we see that in the relational model, and it is required in relational database, so we know that we might as well make our design from an ER perspective fit that right from the beginning. I mean, we can build in stuff if we want, but it just causes us work in the conversion process. And so this and multi-valued, I'd say every value needs to be atomic, and multi-valued attributes are not allowed, right? We don't have those in relational database. I don't expect to see those in these models. You know, people will say that, well, the object models allow us to do that. But yeah, but if we know we're going to implement a relational database, why bother doing it? It's not going to make the model that much more complex in most cases. And so I would make the model have the additional entities. Well, so here's an example, which I guess you look at it and you say, well, golly, what's the difference between this and a relation? And I guess the fact is that there is not much difference, right? So if we, I like red. So we have a key, and so here we have the class table. And we see it has a class code, a course code, a section, a class time, a room, and a professor number. And as you look at this, I think you probably can see that some of these things, the primary key, class code, makes perfect sense. See, it's unique across all instances of shown here. Right? And then we have course code, which looks like a foreign key, where the course code of ACIS5504Chapter4LectureRecordingFinal probably identifies some instance of an entity course. But is it the same as a relation? Absolutely, exact same thing. Well, so multi-valued attributes and multi-valued groups of attributes require creating a new entity with those attributes, and then requiring the key of the new entity to be a foreign key in the original entity. This way you maintain the relationship between the original entity. Say the original entity was student, and the multi-valued entity was, or this time it would be a repeating group. So the multi-values of course number, semester ID, and grade was repeated within student for every course the student had taken. So now what we need to do is we need to take that, make a new entity called student course, or some brilliant name like that, but some new name, right? And where each student has many student courses, and each student course is for one and only one course. And so that way we would have a new entity and a foreign key to the original entity. Well, derived attributes are those that can be calculated from other attributes. And what I would say is you only really want to do a derived attribute. You can model derived attributes if you want. If they are derived from the same instance or from one instance of one entity, I think I'm okay with derived values in that case. Once you start moving beyond that, and say you want to have a derived value of the invoice sum for a customer, and you're going to derive that every time at runtime, I'm not too keen on that. On the other hand, this is not the time to think about those things. It's not the time to think about whether we should have an attribute derived or any kind of how we're going to do things. This is the time. ER modeling is we're trying to say is what is the solution to the problem. And that is our focus. How things work and things is a less of an issue. Well, so here's an example of the perfect type of attribute that should be derived, right? You know, employee age is always changing, but employee date of birth never does. So employee age is something that can be quickly calculated from the date of birth, which is stored in the current date. So it should never be stored. It comes, I guess these values, I guess, don't come all from one instance of employee, but the other current date is always available. So that's your waypoint for deciding when to derive and when not. Derive when all of the data comes from one instance. When it's something beyond that, then you have to do a more careful consideration of when to derive, because it really increases CPU cycles, which means it slows down your system, and then you also have the complexity of writing the code. And there I'm saying something like calculating the employee hours per year or something like that. So I don't know, it would be a different calculation, not associated with date of birth. But anyhow, the idea is be careful deriving things when it involve calculations across multiple rows of tables. When you have something to derive that all comes from the same row or the same instance, it's best to derive those. Well, relationships are definitely the most important idea in relational database. And we already talked about how keys and foreign keys are the way relationships are implemented. And so this is one of the critical ideas of ER modeling, because in my ER model, I really only want to see two things: entities and relationships among entities. And so this idea that entities participate in a relationship and that all relationships are implemented with foreign keys is a key concept. Well, there's a couple of sort of terminology issues associated with relational database and with ER modeling, and these are associated with how many instances of one entity are associated with another instance of another entity. And that is this idea of connectivity. What we do is when we have two entities that are related to each other, we say that entity A, one instance of entity A, is related to how many instances of entity B. And it can be related to 0, 1, or many instances of entity B. And so this idea of connectivity is defining those relationships among the entities. And then cardinality is when you go to a little more detail on connectivity. Instead of saying that one instance is related to many instances, you can say one instance is related to 10 instances or 4 instances, or you can just go with many. And so they implement concepts from the problem domain, known as business rules, where there is a situation in the world that is true, right? Like each order is placed by one and only one customer. So here's an example of connectivities and cardinalities. Connectivity is the idea of one instance of professor teaches one or many instances of class. And of course, I like to read these backwards, where one instance of class is taught by one and only one instance of professor. Now, that's the connectivity. The cardinalities are when you actually specify the min and the max. And here, we see that there is a max in this world on what the number of classes a professor could teach. Well, dependence is this idea that an entity, some entities, can't really exist until another entity exists. For example, an employee dependent couldn't exist until there's an employee. What that means is there must be an instance in the employee entity before there is an instance for that employee in the dependent entity, employee dependent entity. And that is sort of the simple idea of dependence. Now, most entities are independent. They exist whether any other entity exists or not. And that's the dominating type of entities are independent. But occasionally we have dependent entities. And I'm not too hung up on this concept. I think the most important thing is you have all the entities you need for your system and all of the relationships, or for your problem, and all of the relationships between them that are in the business rules associated with that problem domain. But it is true that some entities are like weaker and only occur when another entity occurs. Well, so here is sort of how we model this. And so one instance of employee has many instances of dependent. So if we're down here on our crow's foot model, right, one instance of employee has 0, one or many dependents, and one instance of dependent has one and only one employee. So a weak relationship means that you're not identifying the strong entity. And so what you could do is you could make the primary key of the strong entity a foreign key in the weak entity. And that's what it means if it's weak. But if you take that foreign key and then make it part of the primary key of the weak entity, now you are identifying the instance of the strong entity associated with this instance of the weak entity. It's important to remember that all relationships and all relational databases are implemented by keys and foreign keys. What's different between weak and strong is whether that foreign key is part of the primary key of the dependent entity. And so here's an example where it is a weak, non-identifying relationship. And this is the key issue. That the foreign key here, course code, is not part of the primary key of the entity class. And you can see, so here is our course code in course, and here is our foreign key course code. So you can see that one instance of course is related to many instances of class. And what that gives us is the idea that we need to have the relationship. And of course, the one-to-one relationship is given by the idea that we can only store one value for each instance of class in our course code to make our relationship to the appropriate instance of course. That, to me, is the really important part. That's the part you have to get right. Whether you decide whether this foreign key is going to be part of the key or not is a less important issue than making sure that you have all the right keys and foreign keys to make the relationships necessary to solve the problem. So here you can see the difference is that now the course code is both a foreign key and primary key in class. And that makes it an identifying relationship. That way, it is part of the key that makes it that makes the relationship. And to me, these aren't that different. But chances are you'll have a policy somewhere where about how to do this. And here you can see that some of the implementation is slightly different too, in that now, since there's a combination key, these values have to be combined to be unique across all instances, but they are. Again, I'm not too hung up on which one is right or wrong. Probably you have a policy wherever you are. Let's see, my normal approach. I think for class, I would probably go with like a unique primary key like we do here in terms of our index number for all of our sections, and then all these things are really primary keys. So we're not using an identifying strong relationship in the Virginia Tech registration system. Well, so if you wanted to, you could have a weak entity dependent in a strong relationship where the key of dependent includes the key of the independent entity, employee. And so these kind of things are interesting, but what's important is you know which instance of dependent is associated with which instance of employee, and for each instance of employee, how many instances of dependent are associated with it. Well, participation is the idea that there are more than one entity in a relationship, and how many entities participate in a relationship is the order of the relationship, but we'll get there later. So sometimes there's relationships which are optional, 0, 1, or many, and so most of the time we want to have a mandatory participation whenever we have keys and foreign keys, but we need optional participation to really show the semantics of how the data get into the system. That is usually where optional ends up occurring when we are looking at this idea of which instance of an entity comes first. And so again, this is another thing that is commonly referred to, but to me is not that critical. Usually you want everything to be mandatory, except when it has to be optional. But overall, the final ruling decision-making idea is, how does it really work in the true world? And then try to model that as accurately as we can. Well, there's our notations. Optional, 0 or 1. Many, 1 or many. 1 and only 1. I think most 80% of your relationships will probably be 1 and only 1 and 1 or many. Because we already talked about how when we have a many-to-many relationship, we have to break that down. So here's some sort of idea that where the world should decide which of these is true. Is it true that a course generates 0, 1, or many classes? If that's true, why do you even have a course? Or does a course generate at least 1 or many classes? Now, it seems to me that maybe if class is defined as per a semester or something, then there'd be some courses that don't have any courses. But usually if you have a course, it should have at least had 1 class at some point in time. And so you can see that the semantics of the problem, even in this trivial situation, don't always come out perfectly obvious. And that's a lot of what we spend our time as designers thinking about and debating, is what is the real truth of the world. Should there be a course that doesn't have a class? If you really get down to some technical details, is it okay to have a course with no class, or is it actually required? If you think about it, if we have a referential integrity issue, right? If we have an instance of class, there must be an instance of course that precedes it. So that means that on a brand new course, there's going to be an instance of course before there's an instance of that course implemented as a class in a semester. So 0 could be the most accurate representation of the world. Rarely does that level of subtlety help us much in terms of making our system work. But in the spirit of modeling everything we know, we ought to include it. Well, the degree of a relationship is the number of entities that participate in it. And so a binary relationship, which is sort of the dominant ones that we will work with, and ternary relationships, also ones that we work with a lot, are different in that binary has 2 entities on the relationship, like those ones we just saw where one instance is related to many instances. And ternary relationships are where the relationship is really among 3 entities in the model. And finally, we have sort of a special case, a unary relationship, where that means that one instance of an entity is related to other instances of that same entity. And what this enables is a hierarchical recursive relationship, which means that whenever we have one instance of an entity that points to another instance of an entity, so what we're saying is the primary key of an entity is stored as a foreign key in that same entity, such that an instance of an entity can be related to other instances of that same entity. And it's really an interesting phenomenon when you start to understand it. For example, if we had an employee entity, and of course that entity would have a primary key of employee ID, and we added an attribute to this entity to allow us to show the relationship between an instance of the employee entity and the instance of the employee entity that manages that employee. That is their manager ID. So their manager ID would be a foreign key to employee, even though it's an attribute of employee. And there we would store the value of the employee ID that manages an instance of the employee. So if we had the my manager ID, right, I would be in this employee table and I would have an employee ID, and my manager would be in this employee table and he would have an employee ID. And what we would do for my instance of employee with my employee ID, we would also have an attribute, a foreign key of manager ID, and in there we would store the value of the employee ID value of the instance that comes from my manager. And this is really, I think, an interesting way of modeling when there are naturally occurring hierarchical relationships in the world. Unary relationships are really strong for modeling them. Well, there is a unary relationship right here in the top of our slide. Let me get out my highlighter instead of my pen. So our unary relationship, one instance of employee manages 0, 1, or many other instances of employee. An instance of employee is managed by 0 or 1 managers. Well, that's only 0 or 1 because we must have the top manager in here who's not managed by anybody. Right? Do you see how like that optional idea plugs into whatever the domain of the world is? Here's a binary relationship. The professor teaches a class, teaches 0, 1, or many classes. The class is taught by one and only one professor. Here's a nice ternary relationship where we have a doctor, a patient, and a drug, and we have a prescription. A doctor prescribes many patients. A doctor prescribes many drugs. Interesting here, and we talked about many-to-many relationships in our prior relational model analysis. And here, with this ternary relationship, we do something similar. We create a new entity and new one-to-many relationships to replace the many-to-many relationships between the doctor and patient, and then doctor and patient and drug. And so we have this new entity, prescription, and each doctor writes many prescriptions, each patient receives many prescriptions, and each drug is used for many prescriptions, but each instance of prescription identifies one and only one doctor, one and only one patient, and one and only one drug. That's a really good example of a ternary relationship. And of course, at any one point in time, there could be some doctors that haven't written a prescription, although you would think that'd be highly unlikely these days. Similarly, there'd be some patients that aren't receiving any prescriptions. They don't need any drugs. And then there are some drugs that have yet to be approved or to appear in prescriptions. These are ER models and the examples of relationship degree. So here, where we have the implementation of our ternary relationship, the key thing I think to see is that prescription, and I guess you already knew this because of the one-to-many relationships there, is prescription really has a foreign key for each one of the other entities in the relationship, for each one of the relationships that are ternarily related, right? Each instance of prescription tells us what doctor wrote a prescription for which patient and what drug that was for. Now, it also tells us the date the prescription was issued and then some dosage information. And similar to the many-to-many relationship, where we created a new table and two one-to-many relationships to implement it in a relational database, here what we would do is create a new table and three one-to-many relationships as shown previously. Well, this is an example of a ternary associative entity, prescription is, but we also know to decompose our many-to-many binary relationships into a new entity and two one-to-many relationships. Often these new tables or relations entities have a composite key that includes the primary key of the other two entities as its pieces. And so often, although to me it's really important to look for additional attributes whenever you identify one of these bridge or association entities, like prescription. Right? In prescription, there was a prescription date and then some other text information. But anytime you identify a many-to-many relationship and then you break that many-to-many relationship up into a new entity and two one-to-many relationships, you should really carefully ask yourself, does that new entity have any other attributes? Well, so here is the sort of the relational side. This is more of a relational model to me. So we have a student has many classes, and a class has many students. And so what we see is that this student has two instances, actually has three instances of enroll, meaning that he's enrolled in 3 courses, while the course an entity of course, this particular entity of course has 2 instances of enroll. And you can see that each instance of enroll connects to one instance of class and to one instance of student. And we can see that Bowser liked 10018 more than he did his other 2 classes. Well, so here's an example. Of this here's just the same example, looking at it as a model, right? Where a student enrolls in many classes, a 0, 1, or many classes. A class is enrolled in by 0, 1, or many students. So I make a new composite entity enroll, and I say one instance of student is written in many 0, 1, or many instances of roll. One instance of roll is for one and only one student num. A class is found in many enrolls. I don't like is found in. Is taught by many enrolls. Well, maybe not taught by, includes many enrolls. And so now we had a many-to-many here, and we've come up with a new entity and 2 one-to-manys here. And that's how we implement a relationship in a relational model. So I'm saying that even though I know you're really smart and everything, and you can handle many relationships in your models, I would say only do it whenever you get to a number of components of the model where it gets really complex, which probably isn't going to happen in this class. Well, so here's a list of the entities in the university system. We have school, or the list of the relationships in the university system. So we have the school operates a department. A department has one or many students. A department employs one or many professors. A department offers one or many courses. A course generates one or many classes. A professor is dean of one and only one school. A professor chairs one and only one department. A professor teaches one or many classes. A professor advises one or many students. A student enrolls in many classes. A class enrolls many students, many-to-many relationship there. Building contains one-to-many rooms. A room is used for one or many classes. And so you can write your relationships down like this, in addition to putting them in a model. I don't usually spend time on this. I go directly from the model into the database. So here's what the model should look like. And so if we sort of walk through it, take a starting point somewhere in the model, and I guess upper left is as good as any. So here we have professor, and we see a relationship which is a one-to-one relationship, where professor is dean of a school, 0, 1, or many schools, because not all professors are going to be a dean. Only one out of many, over 100. So a school is headed by one and only one professor, who is the dean. And then, so if we also then move from professor, we also have a one-to-one relationship between professor and department, where a department is similar to a dean. A professor chairs 0 or 1 departments, and a department is chaired by one or many, or one and only one, professors. Now we also have a relationship between professor and department. Each professor is employed by one and only one department. A department employs one or many professors. As we work our way around the relationships of professors, we see that a professor teaches 0, 1 or many classes. And a instance of class is taught by one and only one professor. A professor advises 0, 1 or many students. A student is advised by one and only one professor. So now as we worked our way through our model, we're able to understand how professor fits into relationships with other elements of the model, other entities. Well, to continue, the school operates one or many departments. A department is operated by one and only one school. A department offers 0 or many courses. A course is offered by one and only one department. A department has 0, 1 or many students. A student majors in 0 or 1 majors, or what are offered by departments. You know, has is like a weasel word. I don't like it. But it's not always that clear. Department has majors for 0 or many students. Students, departments, majors in. Something like that. There has to be a better set of words there than has. Now, if this is your model, and you got like one has, and all the rest of these are perfect, there's no points lost, but I just don't like has and is for. But those are sort of the default words. When in doubt and you don't know anything else, you can use has and is for. I really like this model because it has the relationships in both directions labeled. So let's see. We just did our department has majors, and we did courses. A department offers 0, 1 or many courses. A course generates. This is where we are, I think. One instance of course generates 0, 1, or many instances of class. An instance of class is generated from or by one and only one course. We don't want to put too much processed language in our ER models. We want to be careful with that. But we really want to express the problem meaning of the relationship. That's the key idea when we're evaluating these diagrams. All right, so a class is scheduled in one and only one room. A room is used for 0, 1, or many classes. A room is located in one and only one building. A building contains 0, 1, or many rooms. See now, as you're going through here, how could a building contain 0 rooms? I don't, that's where your optional, mandatory kind of thinking is not all that clear. But here, in the relationship between a professor is dean of 0, 1, or many schools, that's a really nice optional thing to indicate, because the majority of the instances of professor aren't going to have a value, or are not going to have a value, or are not going to be heads of schools. There's not going to be any value, right? Because the foreign key is not in professor. The foreign key is in professor num, as it makes sense. I might even not be that keen on this name, right? I would go dean _ professor num, something like that. But it is nice to know that the professor num is the same thing, and this is just an example for learning purposes anyway. So here we are. We're now down to class is found in 0, 1, or many in roles. Yeah, if a class is found in. I don't know about that. That doesn't appeal to me. But, my impulse is to do what I just said not to do, which is put in a has in there. A class has enrolls. Now, I don't, a class has is found in. I'm not that keen on is found in. But this is the implementation of the many-to-many relationship between student and class that we had in the previous slide there. So this many-to-many is replaced with a new entity in 2 one-to-manys, right? 1 to many. 1 to many. So this is that implementation. Right, so a class has enrolled, maybe we could go with that, 0, 1, or many enrolls. And a roll is in one and only one class. And they use contains. And a roll contains one and only one class. That doesn't make sense to me, but that's all right. A student enrolls by 0, 1, or many enrolls. An enroll is for one and only one student. That makes sense to me. But overall, this is a very nice model. Of course, I probably wouldn't have the attributes and make it a little bit less busy. But here you can see all the foreign keys, right? You can see that in this one-to-one relationship has implemented by a foreign key there. This chairs relationship is implemented by the foreign key here. The one-to-many relationship from department code to school is implemented here. The one-to-many relationship, one instance of department, employees, many instances of professor is implemented there. I'll leave as exercise, I guess, to go through and look at the rest of those keys. I'm totally expect you will be able to do it perfectly. Well, it's not always that easy to decide how to create the model. And I'd say in the modeling point, you don't want to make any compromises, right? What you want to do when you're making your ER model is not think about compromises till later. Get the perfect solution. Once you have the perfect solution, then come through and worry about design standards. Your work has to match whatever the criteria are where you are. You have to match it. It's just part of the job, and it's a good thing. And hopefully you'll be assigned to some maintenance task early in your life, and you'll see what a difference quality documentation makes. The first thing is get the problem right, or get the solution right. Be willing to understand the problem to enough depth that you're sure that you have the correct solution. Worry about that stuff, the processing speed, things like that, when you get down further into the actual DBMS. Well, I guess we're almost done. The ER model, to me, is the most important idea. As we said, it's made up of entities and relationships, and then all the attributes that are necessary to keep track of all the data. It makes a perfect translation between what you do in the ER model into a relational model, which of course then translates directly into implementation in a relational DBMS like Oracle or SQL Server or Access or others. The main thing that you have to think about once you identify entities, and the entities usually appear relatively straightforwardly in the problem, like you'll see whenever we do a sample problem live in class. And those are based on the problem. You should be able to observe them in the problem domain. These business rules that tell us how many instances of one entity are associated with another instance of another entity. And many-to-many relationships are certainly valid. Maybe they make your models appear a little bit less complex, and that's okay once you're a super designer. But for now, I just assume you model over all your entities, and that means I want you to decompose your many-to-many relationships. Once we make a model, right, this diagram is our means for communicating between us and other members of the team. It shows what we've decided upon is going to be the world. And so we want to spend our time debating the truth of the world and whether our ultimate model represents exactly what is happening in the world or not. And that is that's our mission, to match the world as truly as possible. And I would say don't compromise in the requirements phase, or in this phase of deciding how to solve the problem. It is important to define the problem completely enough so that you can solve it, but don't make compromises at the requirements stage unless something's really out of whack. And so get your solution right using these ER techniques, and then it's a relatively straightforward process to translate from the model into the database. All right, I think that's about done, and we'll see you in the forum.